In this highlight video, we're going to discuss probably the most important of oxidation reactions, and that involves the oxidation of alcohols. After you've watched this video, you should be able to compare different methods to oxidize alcohols, particularly what their products would be and what selectivities different oxidizing agents have. Let's look at some general outcomes first. When we oxidize a primary alcohol, we lose an H off of the oxygen and an H off of the carbon that bears the oxygen, forming a pi bond to give us an aldehyde. All right, the aldehyde, though, can oxidize again, in this case, inserting an oxygen to form a carboxylic acid. A secondary alcohol can lose the H on the carbon bearing the alcohol and the H on the oxygen to form a carbon-oxygen double bond. In this case, it's a ketone. And if we start with a tertiary alcohol, there's no reaction. Okay, so what's the trend here? All right, what we see is that alcohols can be oxidized as long as they have a hydrogen on the carbon bearing the oxygen. Okay, so primary alcohols can oxidize once. The aldehyde has an oxygen attached to the carbon bearing the oxygen. It can oxidize again. Secondary alcohols have one hydrogen there. They can go to a ketone. The ketone has no hydrogen on this carbon, so it doesn't get oxidized further. The tertiary alcohol has no hydrogen at this position, so there's no oxidation reaction. The oxidation product sometimes depends upon what oxidizing agent you use. So we have divided our oxidizing agents into strong oxidizing agents. The primary one we're going to look at is chromium trioxide. We can also use sodium dichromate here and sulfuric acid. Essentially, these two also give us chromium trioxide. All right, so we got the strong oxidizing here. Down here, we're going to look at weak oxidizing agents. We use PCC. Remember, that's pyridinium chlorochromate. When we oxidize a primary alcohol, just like we saw in the last slide, with a strong oxidizing agent, it gives us an aldehyde. That aldehyde immediately gets oxidized further to a carboxylic acid. We cannot stop at this stage, at the aldehyde stage. If we oxidize a secondary alkyl halide, our product is a ketone. Because there's no H on that carbon bearing the oxygen, it stops there, doesn't go further. If we use the weaker oxidizing agent, that's where we can stop the reaction of the primary alcohol after a single oxidation. So we can stop with PCC at the aldehyde. Okay, it doesn't get further oxidized to the carboxylic acid. For PCC with a secondary alcohol, we still get the ketone. Okay, so for secondary alcohols, it doesn't matter whether we use the strong or the weak oxidizing agent. For the primary alcohols, if we use a strong oxidizing agent, we get a carboxylic acid. If we use a weak oxidizing agent, we get the aldehyde. let's take a look at the mechanism of this chromium trioxide oxidation. The first part of this R group, could either be H, so that in that case it would be a primary alcohol, or it could be an alkyl group, so that would be a secondary alcohol. It's going to be the same for both of these. First step is that the alcohol oxygen attacks the chromium. These chromium oxygen electrons go up onto the oxygen like this. This gives us the H is still here, chromium O minus up there, double bond, plus. All right, so I'm going to show this in one step. It doesn't necessarily have to happen this way. It could happen in two steps, but I'm going to show the oxygen here gets protonated, and the oxygen with a plus gets deprotonated. So I'm just going to show this as a single proton transfer. It could be that the solvent picks up one proton and then delivers another one in two separate steps, but just to simplify things, I'm going to do it this way. Okay, so then we have this OH like this, and so everything's neutral. So now the next step is really the oxidation step. In this step, water, which is going to be our solvent, acts as a base, pulls off the proton that's on the carbon bearing the oxygen, and we do a sort of elimination reaction. Pulls off that proton, we form the carbon-oxygen pi bond, and the chromium can come off. We get from this HCrO3 minus. Okay, so notice in this process we're going from a chromium plus 6 to a chromium plus 4. So the chromium has been reduced, but the carbon here has been oxidized from the alcohol to the ketone or aldehyde. Now, if R equals an H, so if this is an aldehyde, this reaction can continue. Now, the second step is that the aldehyde reacts with water. And I'm not going to really show you this step yet. You'll learn this in next semester. So we get the addition of a water molecule like this. So this is called a hydrate. All right, and now we're going to oxidize one of those two OHs. So I'm going to simplify some of these steps. We have chromium trioxide reacts again. In two steps we'll get to here. And then the elimination step takes place. So the same step that we saw before, like this. And notice what this gives us. This goes like this. We made the pi bond here, and we have an OH remaining. So we've oxidized the aldehyde via this hydrate to the carboxylic acid plus HCrO3 minus. Another interesting thing here is that chromium trioxide up here is actually orange. Okay, but the chromium 4 species over here is green. All right, and so we can see the progress of the reaction by this change in color. And in fact, it shows in your text how they use this color change as a test for alcohol on people's breath if they've been drinking and driving, perhaps. Let's apply some of the reactions that we've learned to synthesis. This is where all of the reactions we've learned over the last couple of chapters are going to really come into play. So in this problem, what we want to do is convert acetylene into this carboxylic acid. So we can take it either in a forward synthesis direction or in a retrosynthesis direction. So let's kind of use a combination of those two. So the first question I'm going to ask is, how can we make a carboxylic acid? Right? From what functional group can we make that? All right, so one way that we've seen in this chapter is the oxidative cleavage of an alkyne. So if we have this alkyne and we use ozone in water, remember it cleaves that and oxidizes that to the carboxylic acid, and it gives off CO2. All right, so that's one good way to make a carboxylic acid. What's another way to make a carboxylic acid? All right, another way is to oxidize a primary alcohol with a strong oxidizing agent. In this case, we could have this alcohol. If we draw this in the synthetic direction, we could use CrO3. All right, so the first option here is perhaps the easiest one to see how we're going to get there from acetylene. Right, so we only have one other step here. We need to do this extension reaction. We add NaNH2-. Remember that deprotonates acetylene to form the acetylide anion. We want to add 3 carbons to that, so we want to add something like bromopropane, and that's going to add on that chain. We then do the ozonolysis, and it directly gives us the product, right? So in only 2 reaction steps. So how can we use the other method? We want a primary alcohol over there. So let's continue our retrosynthesis. How can we make a primary alcohol? Well, one way that we can make it, if we think back a ways, is from an alkene. What conditions would put the alcohol in the end? Right? Remember, this is the hydroboration oxidation. Right, so that does the anti-Markovnikov hydration reaction. Puts an OH on the end and an H at the more substituted position. All right, but we need to get back to an alkyne, right? So let's do one more retrosynthetic step. We could get back to this alkyne. How do we convert an alkyne to an alkene? All right, we have 2 ways to do this. There's no stereochemistry that we have to worry about, and so we could use H2 and Lindlar catalyst, or we could do the dissolving metal reduction. Both of these would reduce the alkyne to the alkene. All right, and then I think the last step should be kind of obvious. We do a different extension step. It's called an alkylation because we're adding an alkyl group, but in this case we want to add 1 fewer carbons. So we just had bromoethane, we had the 2 carbons, we get that chain, we reduce the alkyne, we do the hydroboration oxidation, and then we oxidize the primary alcohol up to the aldehyde. Are there other ways? Well, probably. I'm thinking of another way that I just see right now. I'm just going to do this kind of quickly. We could go from this alkyne, we could hydrogenate it to this alkene, right? We could do an ozonolysis, which is going to get too crowded in here though, would give this aldehyde. And then we could use a strong oxidizing agent to oxidize the aldehyde to the carboxylic acid. Right? So I like problems where there's multiple ways to do it. And any of these approaches would be just fine on an exam.